Okay, so part two of our discussion of limits is going to be regarding finding limits with just the equation given. Keep in mind that when we have an equation, we could certainly try to graph the equation and look at it from a graphical standpoint like we did in the first part. Okay, but the question is there a way to find the limit without actually having to do all that in terms of graphing? Because we know it takes time to graph functions, especially if it's a complicated function. It's kind of time consuming to have to graph everything. So the first point I have over here on the right is essentially the set of directions that we'll use to figure out whether or not we can find a limit when we have an equation given. So the first thing is just a direct evaluation. Okay? Can we directly evaluate the limit? So take a look at the example I have here. I have the limit as x approaches -4 of x plus 3 to the 1998th. And you notice that that's a function that's probably not going to be very easy to graph. Okay? The calculator will even do a power that big. Okay, bottom line here, though, is if we use direct evaluation, can we find a limit here? And all we mean by that is, can we take the x value in question, plug it into the equation, and get a valid answer? Well, in this case, what would happen if we did? We'd have -4 plus 3, that's -1. And -1 to the 1998th power is going to be what? It's 1. So, therefore, since we plug in the -4 and we get an answer of 1, okay, then we can say, yeah, the limit is 1. All right, so if any function, at any point, whatever the point in question is, whatever the function is, okay, if we can directly evaluate it, in other words, if we can plug the x-coordinate in to the equation and get an answer that is valid, okay, or a number, then we can say yes, we can use direct evaluation for that. Okay. Now, let's take a look at this example. We have y squared plus 5y plus 6 over y plus 2, and we want the answer as y approaches 2. Okay. So the question is, can we find the limit of this, okay, without having to graph it? Okay. In this particular case, if we try to directly evaluate it, what happens? Putting a 2 into the top, we'd get 4 plus 10 plus 6, which is 20. Putting a 2 in the bottom, we get a 4. 20 divided by 4 is 5. So the answer is, yeah, we can directly evaluate this because if we put in the 2, we get a valid answer. Now, one of the things that we might be asked, though, it would be similar to this problem, but not quite the same. Okay, same equation here that we're using. But what if I had changed this to a -2? Okay. Then what would be the issue if we tried direct evaluation here? We'd have 0 on the bottom, exactly. So can we always do direct evaluation? No. Okay. Can't always do direct evaluation. Okay. And so we have to have a second idea here then, and that second idea is what I have up here on the right. Okay. What we're going to do, if we can't do direct evaluation, we'll always try that first. Okay. But if that doesn't work, then the question is, can we manipulate the expression with some algebra? Okay. And then directly evaluate it. Okay. So manipulating the expression with some algebra and then directly evaluate. Okay. So in this case, notice I did in fact change that problem. I changed it to y approaches -2 for the limit part. And again, we can't directly evaluate. Okay, but here's an example of some algebra that we might be able to do, or after we do it, then we can directly evaluate. Okay. What I could do is I could factor, and that's one algebraic manipulation that I could use. Okay, I could try to factor either the top or the bottom or both, okay, or whatever type of function I'm dealing with. So I could use factoring, and notice in this case when I do the factoring, what happens with the y plus 2's on top and bottom? We can cross them out, and that just becomes simply y plus 3. And now, if it's just y plus 3, now can I directly evaluate it? Sure. If I put a -2 in there, I'm going to get 1. Fair enough? Okay. And keep in mind that we can verify that to ourselves graphically and numerically because we have graphing calculators. If we were to graph this particular function and see if that makes sense, see if the picture agrees with what we're saying that at -2 this function is very close to 1 on both sides. Okay, let's see if that looks to be the case. So if we do our squared plus 5x plus 6 and x plus 2, we put our function in, and I don't know what window I have here, so I'm going to go zoom 6. And lo and behold, even though it's a rational function, polynomial on top, polynomial on bottom, it looks like a line. Okay, and if you remember from our work in Algebra 2 and Pre-Calc, it looks like a line exactly because of this. Okay, because of the fact that the only issue that we have with the bottom here can be canceled. Okay, and that means that graphically, instead of having an asymptote for this function, it should be a hole. Okay, and if we wipe out the hole, then what does it look like? It looks like y plus 3. Well, y plus 3 is a what? It's a line. Okay. So this function is really this line in disguise, except for there's one issue. Okay, it's not really the line x plus 3. We really can't see it on our graphing calculator, but at -2, what's going on at -2? There's a what? There's a hole there. Okay, and again, depending on what your settings on your calculator are, you generally can't see the hole, so you just need to know that because of the algebra part. Okay, but bottom line is we have a hole there. However, if we look at -2, what does it look like the y value is here? And we can zoom in if we want to and see it better, but bottom line, it looks like the y value is 1, doesn't it? And does 1 seem reasonable? The other thing you can do too is look at your table. If I look at my table, go to table set, I'm going to put it on auto. Start at 0. Okay. And if I look at my table here, I'm going to go back to -2 here. Notice that at -2 I have an error like I expect, which indicates the hole, if you will. Okay, and if you look at the -3 and the -1, does this really tell the story of what's going on at -2 with a 0 on one side and a 2 on the other? I mean, if we had to look at, if we just went by this, would we say that there's a limit? Remember, on the left and right of -2, it has to be the same in order for there to be a limit. True? Well, 0 and 2 aren't the same, are they? Okay. However, what if we did this? What if we said, instead of my change in table being 1s, what if I said it's 0.001? And I looked at the nearest thousandths, and I made -2 my middle point. Oops. Whoops, wrong button. Okay, you'll notice that, again, at -2 you have an error. Okay, but what can we see on the left and right of -2? They're both very, very close to what? To 1. Okay. So remember at the beginning of this, I talked about looking at things from 3 different perspectives. Okay, we started out with a graphing perspective, a graphical point of view. Okay, now we've done an algebraic point of view. We found an answer that way. Okay, and we also, if we had set out to begin with, and we wanted to investigate -2, could we have used our table function in our calculator to determine that the answer was 1 also? Sure. It's pretty convincing evidence that from the left and the right we're approaching 1, isn't it? Okay. And so again, I said graphical, algebraic, and the third one was numerical. And this would be a numerical approach, tabular approach. You're looking at a table. All right, questions so far? Okay, I'm going to show you one more algebra manipulation, and then for the homework that you have for Monday, you're going to be practicing this. There might be a technique or two that I'm going to ask you to just give a whirl to and see what you can do. Okay. The next function I want to look at is this one. We've got 1 over 2 plus x minus 1/2 over x, and we want the limit as x approaches 0. So, looking at our x approaches 0 part, first option here for us is to do direct evaluation. But if we try direct evaluation, okay, if we try to put a 0 in there, we have issues. True? Same issue, we got 0 on the bottom. So then, like I said, step 2 is, can we do some algebra here where we could put this into a different form where we could put 0 into it? And ultimately, this takes a little bit of practice, okay, a little bit of experience to decide what to do next here at this point to try to manipulate this. One thing that we already discovered is that we could maybe do factoring. So if it appears there's factoring that can be done, that usually is a pretty good thing to do, algebra-wise. Another good thing to do is when we have something that involves complex fractions, like in this case we have fractions within our fraction, that makes it a complex fraction. Okay. one thing we can do here is to make it a non-complex fraction. Okay, and we learned in Algebra 2 and Pre-Calc to do that by two different ways we could do it. The way that I prefer is to find the common denominator. Okay, for all the fractions present, there's only two of them here. So the common denominator is just going to be 2 plus x times 2. Keep in mind, if I asked you if this was a 3 and this was a 7, okay, the common denominator would be 21, 3 times 7. True? So when we're finding common denominators, we can always use a common denominator as the two being multiplied. So if we do that, if we multiply top and bottom by the common denominator, if you will, and then what happens algebraically? This expression times this expression would wipe out the 2 plus x's. Okay? And this essentially is going to clear our fractions. Okay? So when we do that, we're going to be left with the 2 only. That's where this one comes from, because this expression times this expression wipes out the 2 plus x part, and we're left with only 2 times 1. And then when we do this expression times this expression, the 2's will cancel out, and we'll be left with the 2 plus x in parentheses, and therefore we have this here. A good point to note at this time is that if I didn't put parentheses around this right now, would it still be the same? If I wrote 2 minus 2 plus x and didn't have parentheses, would that be the same? No. And that's one of the most often points lost for people when we're doing calculus, is that we do things like don't put parentheses around stuff when it needs to have it there. Because if you don't put parentheses around there, it's a totally different expression. It's totally wrong. Okay? So we need to be very careful with the parentheses, okay, when we're dealing with anything regarding algebra. Okay? So we got that, and then down here, of course, we have x times the common denominator, 2x times 2 plus x. And then if we simplify that, you'll notice that I have that over here. We have negative x on top, 2 minus 2 minus x. Okay. And then on the bottom, same. And you'll notice I didn't distribute the bottom. Okay. Anybody see why I wouldn't have distributed the bottom? What's going to happen on top and bottom right now if I just keep it like that? What do we have here? We got x and x, don't we? So x and x can be divided by one another. And we wind up with negative 1. And then the bottom is 2 times 2 plus x. Now, again, the whole point in doing this was so that if I manipulate this algebraically, okay, and just change the form of it, okay, now, after I've done that, now can I directly evaluate it? And remember, the limit we were after is when x is 0. So now is it okay to put a 0 in here? So there, what's the final answer then if I put a 0 in there? And that's a quarter, negative quarter, I should say. Okay. And once again, I put a little note on here. Is this checkable with either table or graph? To make sure that our algebra is right? Absolutely. Okay. Questions so far?